Namaskaram. In last class, we have seen mass of a lamina. In this session, we will discuss about center of gravity of a lamina. Okay, we consider a lamina like this, and this is the definition of center of gravity. The center of gravity of a lamina R is the point x bar y bar. In this figure, this is the point x bar y bar, such that the effect of gravity on the lamina is equivalent to that of a single force acting at this point. Okay, that's the idea of center of gravity. That means if you place a point support at this point, then lamina will balance horizontally. That's the meaning of center of gravity. Okay, we have to find this x bar y bar. The idea of proof is like this. Suppose you runs a knife edge along y equal to y bar. Then lamina will be in perfect balance. Why? Because the line y equal to y bar contains the point center of gravity. Okay, that means there is no rotational motion about y equal to y bar. That means net moment about y equal to y bar is 0. And we have one more equation like that. Next, imagine that a knife edge runs along x equal to x bar. It is clear that this line contains the point x bar y bar. So there is no rotational motion about x equal to x bar. Okay, that means net moment about x equal to x bar is 0. So we have two equations like that. By solving these two equations, you can easily find x bar y bar. That's the idea of the proof. Okay. Okay, next you are going to define the moment. If a point mass m is located at the point, suppose there is a point mass at this point, then the moment m about the moment of m about a line measures the tendency of the mass to produce a rotation about the line. Okay, suppose you consider a line like this, suppose y is equal to b, then naturally due to this mass there is a tendency of rotation about this line, and that the quantity is measured using the term moment. Okay, then how to evaluate moment corresponding to this point mass about the line y equal to b, and similarly you can find the moment about some x equal to a. Okay, consider a lamina like this, and this is our x-axis and this is y-axis. Okay, then we assume that a point mass is placed at the point x k star y k star, and we consider a straight line x equal to a. So we can define the moment corresponding to this m about the straight line about the axis x equal to a is defined like this: m into m means the mass at this point, m into this distance, that is nothing x k star minus a. Okay, similarly you can define the moment about y axis, or not y axis, moment about y equal to b, the same, almost same formula, that is equal to m into this distance, that is y k star minus b. Okay. Okay, we know that lamina balances on the lines x equal to x bar and y equal to y bar, because these two lines contains the these two lines contains the center of gravity x bar y bar. Okay, so net moment about x equal to x bar and y equal to y bar, both are 0. Okay, so next we have to find this net moment. Okay, we use the same technique in our double integration. First of all, we subdivide the lamina into small rectangular pieces using the straight line parallel to axis, x-axis and y-axis. Okay, and we consider only the rectangles which is completely inside the lamina. And we assume that there are n such rectangles which are completely inside the lamina. And we assume that the kth piece, suppose this is our first piece, second piece, etc. like that. Okay, and this is our kth piece, and kth piece has area delta ak, and the mass of the kth piece is delta mk. This is our assumption. Also we choose a point x k star y k star, they are from the kth piece. Okay, we choose an arbitrary point x k star y k star from the kth rectangle. Okay, here we assume that x k star y k star be the center point of this kth piece. Then we know that the mass of this small portion, small rectangular portion of this lamina can be approximated using this formula: density function into area of the small portion. That is density at the point x k star y k star into delta ak. Okay, suppose a point mass delta mk at the point x k star y k star, Then what is the moment about x equal to x bar? We know that it is xk star minus x bar into delta mk, right? This is the moment about this point. And we have to find the net moment of this lamina. So we have such n rectangular pieces. So the total moment is approximately equal to sigma k equal to 1 to n xk star minus x bar to delta mk. Okay, and what about the total moment about x equal to x bar? We know that this lamina is balanced on this x equal to x bar. So we know that this total moment equal to 0. Right. That means sigma k equal to 1 to n xk star minus x bar into delta mk is approximately 0. Right. This is approximately 0 because this is approximately equal to total moment, and we know that total moment equals 0. That's why this sum is approximately 0. And we know that this approximation is better when the size of the rectangle is very, very small, or number of rectangles is very large. So the extreme case is limit n tends to infinity, k equal to 1 to n xk star minus x bar into delta mk. And the limiting case is extreme case. Extreme case is equal to 0 because r is negligibly small. Okay, so since the lamina balanced on the lines x equal to x bar and y equal to y bar, sigma k equal to 1 to n xk bar minus x bar into delta mk is approximately 0. Why it is approximately 0? Because this left hand sum is approximately equal to the total moment. We know that total moment equal to 0. That's why this is approximately 0. Okay, and this approximation is better when n is large. So extreme case is limit n tends to infinity. Okay, and okay, one more thing here, we replace this delta mk using this formula. So delta x k star y k star delta mk. So that is again approximately equal to 0. That's all. The extreme case is limit n tends to infinity. So similarly, we have one more result. Okay, this is nothing. This is the approximately total moment about y equal to y bar, right? And we know that the total moment about y equal to y bar is also 0. So that's why this is approximately 0. And next we substitute delta mk using this formula. In next step, we take the limiting process, extreme case. Okay, if n is large, this error is very, very small. Okay, so extreme case is limit n tends to infinity, sigma k equal to 1 to n xk star minus x bar into the mass equal to 0. And we know that what about this infinite sum? This infinite sum is, we can write this infinite sum as double integral like this, double integral over r. Instead of xk star, this become x minus x bar into delta of xy dA. Okay, so we can denote this infinite sum using this double integral. So this double integral equal to 0. Okay, similarly we have one more case, limit n tends to infinity, this sum of moments. This is also 0. That means we can denote this infinite sum using the double integral like this, double integral over r. Instead of yk star, it is y minus y bar into delta of xy dA equal to 0. Now we have two equations. Okay, here x bar is constant. Okay, to solve for this x bar, you can expand this integral as two integrals like this, double integral x into delta dA minus double integral x bar into delta, and x bar is a fixed number. Okay, so you can take outside. So x bar into double integral delta dA equal to 0. Then you can easily solve for x bar. So what is x bar? X bar equal to double integral x delta dA divided by this quantity. First you take this term to right side, then you can divide with this. So x bar equal like this. And similarly, you can solve for y bar from the second expression. Okay. So this is our x bar. X bar equal to double integral over r x into delta dA by double integral over r delta dA, and y bar equal to double integral over r y into delta dA divided by double integral r delta dA. Okay. Also, we know that this denominator. This is, what about this one? Yes, this is the mass of the lamina. Okay, so x bar equal to this integral by the mass of the lamina. Similarly, y bar equal to this integral by mass of the lamina. Okay. Okay, consider a problem. Find the center of gravity of the triangular lamina with the vertices 0, 0, 0, 1 and 1, 0. The density function is the delta of xy equal to xy. Okay. Okay, let x bar y bar be the center of gravity. Then we know that x bar equal to double integral over r x into delta of xy dA by m. M is the mass of the lamina. In previous session, we have seen that density of this lamina, the same problem, density of this lamina, not density, sorry, mass of this lamina is equal to 1 by 24. In our previous session, we have seen this problem. Okay. And so we have to find this numerator. Okay, I'm going to denote this numerator by mx. Then next our aim is to find this mx. So mx is equal to double integral over r x into delta. What is delta? Xy. X into xy dA. Okay. So we have to integrate over this triangular region. So better you consider a vertical strip. So what is the lower value of y? Y equal to 0 up to y is equal to, oh, this is actually y is equal to 1 minus x, right? Equation of the straight line is x plus y equal to. Okay, so this is actually y is equal to 1 minus x. Then this is actually minus x minus 1. Sorry, minus x plus 1. So the integral and the strip is varying from x equal to 0 to x equal to 1. So integral is like this 0 to 1, 0 to 1 minus x square y dy dx. So this becomes 0 to 1 x square y square by 2, 0 to 1 minus x. So when y equal to 1 minus x, this become x square by 2 into 1 minus x whole square. When y equal to 0, the term is 0. So next you have to expand this bracket and multiply. So this become integral 0 to 1 x raised to 4 by 2 minus x cube plus x square by 2 dx. Then we can easily integrate this with respect to x and substitute the limits. Upon simplification, this becomes 1 by 60. Okay. Okay, so x bar is equal to 1 by 60 by 1 by 24, that is equal to 2 by 5. Okay, similarly you can find y bar. So y bar is equal to double integral over r y delta dA by m, mass of the lamina. We know that that is 1 by 24. And the numerator is equal to integral 0 to 1, the same lamina. So again, same limits. Okay. Only difference is this is y into delta. So y into delta means xy square. So its integration is y cube by 3. Then you can substitute upper limit and lower limit. Then this become x by 3 into y cube is 1 minus x whole cube. Next you can expand this using the formula a minus b whole cube. Then this become, okay, so first you expand this bracket and first you expand using a minus b whole cube, then take the product. So this becomes like this. And you can integrate this one with respect to x. So ultimately upon simplification this becomes again 1 by 60. So what is this y bar? Y bar is again 1 by 60 by 1 by 24. It is same as 2 by 5. Okay. So x bar is 2 by 5. Y bar is also 2 by 5. So its center of gravity is 2 by 5, 2 by 5. Okay. Okay. This is your homework. Thank you.